Hello there, Algebra 2s. It's St. Patrick's Day here, so we're going to be using our green pens for you this morning. Let's take a look at these graphs that they gave us. There's only 6 of them to do, but it's sure going to be a lot of thinking for us to get through them. All right, as a review, your vertical asymptote is when your denominator is equal to 0. I see a vertical asymptote of x is equal to 0, so I know I at least have, and I am going to be using a pen while I think my way through, or a pencil while I think I want my way through this. So if I have a vertical asymptote at x is equal to 0, that means that that's going to be the denominator of my rational function. My horizontal asymptote comes in 3 conversations. Choice number 1, if I have more x's in the denominator than the numerator, my horizontal asymptote is y is equal to 0. That is not happening here. When I have the same number of x's in my numerator and denominator, my horizontal asymptote is the fraction of their coefficients, which means that I have, this looks like a horizontal asymptote of y is equal to 1. So here I know that my horizontal asymptote is y is equal to 1. So as I build my function, that means I have the same number of x's in my numerator and denominator. So that doesn't look like much of a function there, does it? So what we're going to do now is take a look at this xy ordered pair that we know is a solution. If I look here, it looks like when x is equal to -2, 0 is an output. So because I know that that is a conversation that's true, when I come down here and I say 0 is an output, when I have a value of -2 in with x. So that means that -2 is for that x. And do you see how that +2 ends up being a necessary part of my function? So if I have x plus 2 in my numerator, that means that an input of -2 is going to give me 0 as an output. So I'm going to go to my graphing calculator and I'm going to see how I did. I'm going to go ahead and say x plus 2 divided by x. And when I graph, I'm going to try and see how do you think I did. Now here's a problem. It looks like I have other issues here. I got this part right, but this ends up looking like my asymptote, or this is exaggerated a little bit. That looks like I had maybe a stretch. So when I go here, maybe I can insert a value of 2 and see if that, when I graph, changes my, do you see how now that stretched this up a little higher? So if we have this value of 2 in front of this fraction, that would work. Otherwise, we can just leave this as a coefficient of a. For the most part, I have my function now because this fits my asymptotes and my x-intercept. Okay, let's take a look at number 2. When we look here, they have here an x is equal to -4, so that's what they want us to use maybe as our test point. I don't know. All right, when we go ahead and I see my horizontal asymptote, my horizontal asymptote looks like it's at y is equal to 0, which when I go to build my function means that I have more x's on the bottom than on the top. When you look here, I have a y-intercept of over 0 down 1. and it doesn't look like I have any x-intercepts. And when I look here, I see a vertical asymptote at what looks like x is equal to +1, which means that down here x cannot equal +1 because that makes that a value of 0. So let's go ahead and play with this. Let's stick a 1 up here and compare our functions. Go to our graphing calculator and we'll go ahead and test it and see if I had 1 divided by x minus 1, what would our graph look like? Pretty good. So this one looks like we hit it spot on. When we look at this x is equal to -4, I can go up here and see that is what is making x smaller and smaller and smaller. So we're going to say that's -0.2. And we'll stick with this as my numerator for that function. These are certainly tricky. It really demands that we look at and analyze each part of these functions as we go. And to be honest with you, a lot of trial and error. So here's an interesting conversation. When x is equal to 0, we can see from this graph y is equal to -1. What's also interesting for this one is I have 2 asymptotes, which means when I go to build my function in my denominator, I know I have x plus 1 and x minus 1 because those are going to be our 2 asymptotes. When I look at my horizontal asymptotes, let's go over here. My vertical asymptotes are x is equal to 1 and x is equal to -1. My horizontal asymptote is y is equal to 0. So because I have 2 x's down here, I either have no x's or I have 1 x. So let's go ahead and go to the graph because we got to play with what's going to make this a possibility. So if I have in my graph 1 over x minus 1 and I add to it, let's see, we have to have parentheses and then another parenthesis, no, not that button, x minus 1 inside this parens times x plus 1, because I want to keep that whole denominator together, so 2 parens. When I go to graph, that's going to give me each of these asymptotes and this curve right there. So it looks like we're okay with having y is equal to 1 over x plus 1 and x minus 1. Okay, so let's check out this next one. It says here that when x is equal to 1, y is equal to 0. I'm glad they clarified because I'm not sure that was easy to see by the graph, but okay, we'll take that. When I look here at my vertical asymptote, I see x is equal to -1. So when I come down to work on building my function, I'm going to go ahead and put an x plus 1 in the denominator. Think about why that is. If x can't equal -1, that's what's going to make this denominator equal 0. All right, let's talk about my numerator. It looks to me like I have a horizontal asymptote, and my horizontal asymptote looks like y is equal to 1, which means that has to be the coefficient of the fractions, which means there's at least an x hanging out up here. So when I look and I put my x in my numerator, that's going to give me a coefficient of 1 when I look at, or a fraction of 1 when I look at their coefficients. And that's also going to give me, let's see if that ends up being when x is equal to 1, my output is not equal to 0. So I'm wondering what we're going to have to do to change that, and we'll set up that equation. So x plus some number a is going to be equal to 0. Think about what I'm doing here. They told me that an input of 1 gives me an output of 0. So when I put 1 in for x and I solve for that a looks like it's got to be equal to -1, which means maybe that is what is in my numerator. So when I go to my calculator to check this out, we're going to go ahead and put x minus 1 in my numerator divided by x plus 1. Okay, so when I graph it, ooh, I'm looking pretty good. Now let's go to the table of values. Do I have x is equal to 1 with an output of 0? Yeah, I'm looking pretty good, which means that I did okay with this function here. My output is equal to x minus 1 over x plus 1. And what I'm doing is I'm building these functions bit by bit. There, maybe you can see it better now. I'm building these functions bit by bit and having some kind of data, vertical asymptote, horizontal asymptote, xy ordered pair that helps me build my values. All right, you're doing great. Let's try to do this fifth one together. Now this is very curious because this sure looks like a linear equation to me. So what I'd really like to say is, it looks like I have an input of 0 and an output of -1. It looks like here I have an input of 1 and an output of 0. So I'd really like to write this linear equation. So I can go ahead and say that my slope is going to be equal to my difference between my y's over my difference between my x's, which means my slope is going to be equal to -1 over -1. My slope is equal to +1. If I want to do y equals mx plus b or my point slope form, I could say y minus y1 is equal to my slope times x minus x1 for my point slope form. Y minus, we'll go ahead and use the easy one here, 0 is equal to your slope times your x minus 1. So y is equal to x minus 1. So that's definitely the equation of my vertical line. But do you remember yesterday when we had some discontinuity and we had some things end up canceling out? Because we're in the rational function unit, I'm wondering if it's one of those ones where I had x minus 1 in my numerator, but what if I had an x plus 1 and an x plus 1 that ended up being a value that canceled out? The reason I'm curious about this one is because if I have a -1 value for x, this tells us that y is equal to -2. But if I'm talking about a rational equation, maybe this is one of those ones with the holes. Maybe this is one of those ones where this -1 makes it undefined. It's a curious conversation. They didn't give us a key, so we have no way of knowing. So we can go ahead and take the easy route and say, oh, that's a linear equation with a slope of 1 and a y-intercept of -1. But I want you to think about and consider what if it was a rational equation that looked like this. Okay, they're telling us number 6 is the challenge. And I don't think this is the challenging one. I think these other ones have been challenging for us. I know that's the equation of when I have a quadratic. When I have a squared in the denominator, I don't see any asymptotes other than y is equal to 0. So what I'm tempted to do is just, or x is equal to 0, what I'm tempted to do is just to graph what I think might be that squared function is what makes that value positive. So when it's squared, whether that's a blown up version of that or not, I don't know. But when they say challenge, I'm going to push back against that because I think some of these other ones were much more challenging. Hey, if you've stuck with me so far, thank you. Congratulations. You're amazing. We're going to give you some math-based ones to fit this one. I think you'll like them. So keep on looking at these functions and analyzing our horizontal asymptotes and our vertical asymptotes. You guys are awesome. Thanks. Bye.